I'm going to define a function s of n, and I'm going to define it as the sum of all positive integers, including n, including n. And so the domain of this function is really all positive integers. N has to be a positive integer. And so we can try it out with a few things. We could take s of 3. This is going to be equal to 1 plus 2 plus 3, which is equal to 6. We could take let's take s of 4. Well, that's going to be 1 plus 2 plus 3 plus 4, which is going to be equal to 10. So fairly straightforward. Now, what I want to do in this video is prove to you, and there's actually multiple ways to prove this, that I can write this as a function of n, that the sum of all the positive integers up to and including n is equal to n times n plus 1, all of that over 2. And the way I'm going to prove it to you, or at least the first way I'm going to prove it to you, is by induction. This will be a proof by induction. And it's kind of an interesting philosophical way to prove something. Because the way you do a proof by induction is first you prove the base case. You prove the base case. So in the case of this statement right over here, so this is what we need to prove. In the case of this statement right over here, we're first going to prove it for 1. That's going to be our base case. And then we're going to do the induction step. The induction step, which is essentially saying if we assume it works for some positive integer k, if we assume that, then we can prove that it's going to work for the next positive integer. It's going to work for k plus 1. And the reason why this works, let's say that if we prove both of this. So the base case, we're going to prove it for, in this case, we're going to prove for 1. Prove for 1. But it doesn't always have to be 1, because your statement might be this is true for everything above 55 or everything above some threshold. But in this case, we're saying it's true for all positive integers. So our base case is going to be for 1. And then our induction step, we're going to try to prove that if you assume that this thing is true for sum of k, if we assume that, then it is going to be true for sum of k plus 1. And the reason why this is all you have to do to prove this for all positive integers is just imagine. So let's think about all of the positive integers right over here. 1, 2, 3, 4, 5, 6. You could just keep going on forever. So we're going to prove it for 1. We're going to prove that this formula right over here, this expression, applies for the case of 1, when n is 1. And then we're going to prove that if we know it's true for any given k, that it's true for the next one. So if we know it's true for 1 in our base case, then the second step, this induction step, says, well, it must be true for 2 then. Because we proved generally if it's true for k, it's going to be true for k plus 1. Well, if it's true for 2, then it must be true for 3. Because we've proven if it's true for k, it's true for k plus 1. So if it's true for 2, it's true for 3. And then if it's true for 3, it needs to be true for 4. And you can just keep going on and on forever, which means it is true for everything. Now, spoken in generalities, let's actually prove this by induction. So let's take the sum. Let's do this function on 1. Well, that's just going to be the sum of all positive integers, including 1, is just literally going to be 1. We've just added all of them. It's just 1. There's no other positive integer up to and including 1. And we can prove that this is the same thing as 1 times 1 plus 1, all of that over 2. 1 plus 1 is 2. 2 divided by 2 is 1. 1 times 1 is 1. So this formula right over here, this expression, it worked for 1. So we've proven our base case. We've proven it for 1. Now what I want to do is I want to assume that it works for some number for some number k. So I will assume true for, I will assume it is true for some number k. So I'm going to assume that for some number k, that this function at k is going to be equal to k times k plus 1 over 2. So I'm just assuming this is true for that. Now what I want to do is think about what happens when I try to find when I try to find this function for k plus 1. So this is what I am assuming. I'm assuming I know this. Now let's try to do it for k plus 1. So what is the sum of all of the integers up to and including k plus 1? Up to and including k plus 1. Well, this is going to be 1 plus 2 plus 3 plus all the way up to k plus 1. Right? This is the sum of everything up to and including k plus 1. Well, we're assuming that we know what this already is. We're assuming that we already have a formula for this. We're assuming that this is going to simplify to k times k plus 1 over 2. We're assuming that we know that. And so we'll just take this part and we'll add it to k plus 1. So we'll add it to the k plus 1 over here. We'll add it to the k plus 1. And if you find a common denominator, the common denominator is going to be 2. So this is going to be equal to, I'll write the part in magenta first. This is k times k plus 1 over 2 plus 2 times k plus 1 over 2. This thing in blue is the same thing as that thing in blue. The 2's would cancel out. I just wrote it this way so I have a common denominator. And so this is going to be equal to, we have a common denominator of 2. And I'll write this in a different color here. So we're going to have k times k plus 1 plus 2 times k plus 1. Now, at this step right over here, you can factor out a k plus 1. Both of these terms are divisible by k plus 1. So let's factor this out. So if you factor out a k plus 1, you get k plus 1 times, we're factoring it out. Over here, if you factor out a k plus 1, you just have a k. Over here, if you factor out a k plus 1, you just have a 2. Let me color code those so you know what I'm doing. So this 2 is this 2 right over there. And this k is this k right over there. We factored it out. These k plus 1s, we factored them out to this k plus 1 right over there. And it's going to be all of this over 2. Now, we can rewrite this. This is the same thing. This is equal to, this is the same thing as k plus 1, that's this part right over here, times k plus 1 plus 1, right? This is clearly the same thing as k plus 2. All of that over 2. Now, why is this interesting to us? Well, we've just proven it. If we assume that this is true, and then you just use that assumption, we get that the sum of all of the positive integers up to and including k plus 1 is equal to k plus 1 times k plus 1 plus 1 over 2. We're actually showing that that original formula applies to k plus 1 as well. If you just take k plus 1 and put it in for n, you got exactly the result that we got over here. So we've proven our base case. This expression worked for the sum for all of the positive integers up to and including 1. And it also works if we assume that it works for everything up to k, or if we assume it works for the integer k, it also works for the integer k plus 1. And we're done. That's our proof by induction. That proves to us that it works for all positive integers. Why is that? Well, we've proven it for 1. And we've proven it that if it works for some integer, it's going to work for the next integer. If you can assume it works for some integer, it will work for the next integer. So if you assume that it worked for 1, then it can work for 2. Well, we've already proven that it works for 1. So we can assume it works for 1. So it definitely will work for 2. So we get 2 checked. But since we can assume it works for 2, we can now assume it works for 3. Well, if it works for 3, well, then we've proven that it works for 4. And you see how this induction step is kind of like a domino, and it cascades, and we can go on and on forever. So it'll really work for all positive integers.